Welcome to Devil's Backbone, which is an open space just west of Loveland, Colorado. We're just north of the Big Thompson River, shortly after it exits Big Thompson Canyon. We'll talk about the Big Thompson River in a little bit, but what we want to talk about here is some of the rock features that we can see. Devil's Backbone, of course, is known for this ridge of rock, which is called the backbone, that we can see over here. In order to understand the Devil's Backbone, we need to understand the entire geologic history for many of the rocks that we see. Most of what we can see from that hill in the distance to this point is sedimentary rocks. And as we know, sedimentary rocks are built up layer upon layer, with the oldest rocks being deposited on the bottom and the youngest are deposited on the top. And most of those rocks are Permian or somewhat younger in age. Now, they are no longer flat-lying. We've talked about sedimentary rocks. They get deposited in flat layers, one on top of each other. But what has happened to these rocks is that they've been deformed, or they've had their shape change. And how they've changed in shape is they are now what's called an anticline. And so the rocks are arched into the sky, but erosion has since removed them. It takes a lot of tectonic force to fold rocks in that fashion. And the tectonic event was the same event that uplifted the Rockies and the Front Range, which is just to our west. And so we know that the tectonic event that uplifted the Rocky Mountains occurred starting about 80 million to about 30 million years ago, with the uplift of the Front Range occupying a shorter time span within that interval. And this anticline formed when we uplifted the Rockies. The collision was far off to the west, approximately in the area of Nevada today, and there's been a lot of complications tectonically since that time. But when we try to shorten crust horizontally this way through collisions, one of the things that can happen is the rocks get arched like this. And then in the recent millions of years, the top of that anticline has been eroded away. And so the rock layers no longer connect because they are now gone in the sky. But let's now turn our attention to the backbone itself. That's one limb or one side of that anticline. And the other side can be seen behind the houses forming the ridge. We can see some radio antennas over there. Well, why does the Devil's Backbone stick up as a fin? Well, it's a conglomerate with lots of chert pebbles. And chert, as you know, is microcrystalline quartz, which means that it's both physically and chemically resistant to weathering and erosion. And either side, both to this side and the far side, are mostly shale units. And shale is very easily eroded and weathered. And so they preferentially get weathered and eroded away more quickly than the ridge of conglomerate that makes up the backbone. So it's left as a fin because the rocks on this side have eroded away and the rocks on this side have eroded away. And on the other side, because it's more resistant to weathering and erosion, it makes up the top of the ridge because the rocks beneath now form a slope because they're more easily eroded. And one of the best places to see the contrasting strength of these rocks with respect to erosion is near the Keyhole, which is a short hike to the north from the parking area. And we can see that area in this photo here, where on the left side we can see sandstones and chert pebble conglomerate associated with the Lytle Formation. And then to the right of the photo we see shales, mudstones, and limestones associated with the Morrison Formation. Here's mostly mudstones, and these are easily eroded away. And in fact, if we look at the boulder in the photo, you can see that that is a block of the Lytle Formation, which has dropped down, and it's protecting the Morrison Formation from some of that erosion, because you can see that there's a little pedestal of Morrison Formation now holding up that boulder. But let's put it all together now And so here is a schematic cross-section looking north. So west is to the left and east is to the right, showing the progression of some of the key features and events that led to what we see at Devil's Backbone today. So first is deposition of the Morrison Formation, mudstones, limestones, shales, and this has been constrained to have occurred at about 155 to 145 million years ago. And then we had deposition of that chert pebble conglomerate and sandstone unit called the Lytle Formation on top of that. And then on top of that is the South Platte Formation. And we know the top of that is somewhere around 100 million years ago. And it's not as simple as just layer cake as I showed here, but this gets us to the big picture of the anticline at Devil's Backbone. There's, of course, additional rocks that were deposited above this, and there's also additional rocks deposited below, but we're just going to focus on these three formations. And then, starting at about 70 million years ago, the tectonic stresses were affecting this area because of the collision to the west, which lead to the Big Thompson anticline. And if you travel north a ways, there's also a fault called the Milner Mountain Fault, which also offsets these layers and formed in response to the crustal shortening. And then since in the recent millions of years, there's been significant erosion, of course, more strongly affecting the South Platte and the Morrison Formation, such that the Lytle Formation is then left as a ridge, which we call Devil's Backbone today. And if we look at a cross-section from the geologic map of the Masonville Quadrangle, this is depicting an area further north where we see the Milner Mountain Fault, but we can still see the Big Thompson anticline. And this gives a more realistic picture of what a cross-section in the area looks like.